The first of the two distributed practice will have us using a limiting reagent and maximum yield of product from all the appropriate data. The first question has lead 2 nitrate, lead with its +2, nitrate with its -1, PbNO3 taken twice, reacting with potassium iodide, potassium who's a +1, iodide who's a -1. When lead 2 nitrate reacts with potassium iodide, a yellow precipitate forms. The pattern of change is known as a double displacement, outers, inners. Lead will go to the iodide, potassium will hook to the nitrate. Consider charges when you rehook. Lead is still a +2, but now it has a new partner, iodide. PbI2 is our first product. When potassium goes to nitrate, they hook by charge. Potassium nitrate is KNO3. When we hook by charge, we then go back to balance. We have 2 units of nitrate, doubling the first here. 2 units of potassium gives us a 1:2 to 1:2 ratio. The solubility chart, hanging above our classroom door, we need to find either of these two to be the solid precipitate. Potassium nitrate, according to our chart, is soluble. According to our chart, lead 2 iodide has that red sign with it. It would be the insoluble precipitate. So here becomes the target as we go forward and look at our question. It asks us how many grams of the precipitate. We had to identify PbI2 as the precipitate to know what product our stoichiometry problem is having us solve for. If we start with 50 grams of lead 2 nitrate, and we'd like to know how many grams of our precipitate form, our target becomes the PbI2, the yellow solid described in the question. But we're also given 75 grams of potassium iodide. If this indeed is the limiting reagent, would have to calculate and find the PbI2. It's 2 separate stoichiometry problems where we simply compare the 2 answers and we'll circle the smallest of the 2 as our maximum yield. So I need a molar mass for lead 2 nitrate. Let's say 207.2. 207.2 on the lead. 14 times 2 on the nitrogen, and 16 times 6, oops, calculator boo-boo, let me rehit, 207.2 plus 14 times 2 plus 16 times 6. I'm finding 331.22. And that's the molar mass of our first reactant. Our target is the PbI2, our want over given ratio, looks like a 1:1. For every 1 mole of PbI2, I have 1 mole of PbNO3 taken twice. The last thing I'll need is the molar mass of our yellow precipitate, the PbI2. Again, lead using 207.2. plus the iodine, which is 127, but there's 2 of them, so I'll double it. I'm finding 461.2 grams is the molar mass of our target, PbI2. Starting with 50 grams, let me hit for us. I have 50 grams divided by 331.2 times 1/1 times 461.2. This answer, 69.6 grams of the lead iodide. We'll do the same strategy and then compare. Potassium has a molar mass of 39 plus 127 on iodine. This molar mass in our first conversion parenthesis for the second step is 166 grams of Ki. That sits under the 1 mole. The heart of this problem has changed. We still want the PbI2, and its value is 1. but now the coefficient is a 2 in front of the Ki, a want over given of 1/2. Same molar mass, we just calculated 461.2 grams of PbI2 in every 1 mole of PbI2. Using the molar mass for Ki, a want over given ratio, and the target 461.2, let me hit for us. 75 over 166 divided by 2 times 461.2, and I'm finding 104, rounding a little bit, 104.2 grams. Clearly one is smaller than the other. The maximum yield we have to identify as the smaller of the two answers, telling us that the lead nitrate was the limiting reagent and the potassium iodide was in excess amounts.